The plate is almost empty. You don't feel full yet, not really, so you finish it. Maybe there's dessert. It goes down easily enough. Then, roughly 20 minutes later, it hits. Not hunger, the opposite. A heavy, uncomfortable fullness that seems to arrive out of nowhere, long after the decision to keep eating was already made. You didn't overeat on purpose. The feeling simply showed up late, after the meeting had already ended. You've probably heard the explanation for this. It's repeated everywhere. It takes 20 minutes for leptin to signal your brain that you're full. It sounds authoritative. It's on wellness blogs, in diet books, in casual conversation. It's also, in an important and interesting way, not quite right. The real explanation is stranger than a single slow hormone. It involves an organ system with its own dedicated nervous system, one large enough that scientists sometimes call it your second brain, and a specific, named physiological phenomenon most people have never once heard of, hiding at the far end of your small intestine. Let's start where the meal actually starts. Your stomach, expanding as food arrives. Your stomach wall contains stretch receptors, mechanical sensors that detect how much your stomach has physically expanded. As food fills it, these receptors fire, sending a fast signal up the vagus nerve directly toward your brainstem. Piece 1. This is genuinely fast. It's one of the quickest satiety-related signals your body sends. The problem is what it's actually measuring. Stretch receptors respond to volume, how much physical space food is taking up in your stomach, not to how many calories that food contains. A large salad and a small milkshake can occupy wildly different volumes while delivering wildly different amounts of energy. Which means this fast, early signal is, by its nature, an imprecise one. It can tell your brain there's a lot of food in here, long before it can tell your brain anything meaningful about how much energy you've actually taken in. For real information about that, your body needs to wait for something else entirely. As food leaves your stomach and enters your small intestine, it encounters roughly 500 million neurons lining the walls of your gut. A network dense enough and independent enough that researchers have given it its own name, the enteric nervous system. Your second brain, quite literally embedded in your digestive tract. This system does far more than move food along. It detects exactly what kind of nutrients have arrived, fat, protein, sugar, and triggers the release of specific hormones directly in response. Piece 2. One of the first of these is cholecystokinin, or CCK, released within minutes when fat and protein reach your upper small intestine. CCK acts fast, slowing digestion, triggering a real immediate sense of fullness, communicating directly with your brainstem, partly through the same vagus nerve pathway as the stomach stretch signal. If CCK acted alone, the story might end here, close to the 20-minute mark everyone talks about. But CCK is an early responder, not the main event, and there's a reason the fullness feeling keeps building well after CCK has already done its job. Here's the part almost nobody talks about, and it's the actual center of this story. Further down your small intestine, much further, near its end, close to where it joins your colon, sits a stretch of tissue called the ileum. And the ileum has its own trick. When nutrients, particularly fats and certain carbohydrates, physically reach the ileum, specialized cells there release two more hormones, peptide YY and GLP-1. These don't just contribute to fullness. They actively slow down how fast food moves through your entire digestive system, effectively putting a brake on the whole process. Researchers have an actual name for this: the ileal brake. It's a real, well-documented physiological reflex, not a metaphor. A mechanism that exists specifically to prevent food from rushing through your gut faster than your body can properly process and absorb it. Piece 3, and the real reveal of this story. The fullness you feel later in a meal isn't simply a hormone finally catching up. It's your body physically waiting for food to travel far enough down your digestive tract to trigger this break. A delay built into the actual geography of your intestines, not just the speed of a chemical signal. Which brings us back to leptin, and the popular explanation we started with. Leptin is real, and it's genuinely important, but it isn't a meal-to-meal signal at all. Leptin is released by your fat cells, and it reflects something much slower and bigger: your total longer-term fat stores, changing gradually over hours and days, not minutes within a single meal. Leptin tells your brain roughly how much fuel you have banked overall. It has almost nothing to do with why you feel full 20 minutes after finishing dinner. That story belongs to CCK, to PYY, and GLP-1, and to the ileal brake. A completely different, much faster system, operating on a completely different timescale than leptin ever does. So why does a popular but slightly wrong explanation stick around so persistently? Likely because a hormone takes 20 minutes is a simple, tidy story. One slow signal, one clean number. The real explanation is messier and, honestly, more interesting. Multiple hormones, released in sequence, at different points along a tube roughly 20 feet long. Each one triggered only once food has physically traveled far enough to reach it. Which explains something else that's always felt strange: why eating quickly seems to make overeating so much easier. If you finish a large plate in 5 minutes, you can physically consume far more volume and far more calories than your ileum has had time to receive, process, and respond to. The early, imprecise stomach stretch signal is the only one that's had a chance to fire. The more accurate, longer distance signals are still, quite literally, in transit. By the time they finally arrive, often close to that same 20-minute mark everyone's heard about, the amount of food already eaten may be considerably more than the body would have chosen if it had been given the time to hear from every part of the system. None of this means fullness signals are unreliable or broken, or that everyone experiences this delay identically. Individual differences in gut motility, meal composition, and overall health all shift the exact timing involved, and the true range in research spans anywhere from roughly 10 to 30 minutes, depending on what's actually eaten. Highly processed, energy-dense foods in particular can deliver a large number of calories in a small volume, meaning the early stomach stretch signal underreports the situation even more than usual. But the underlying architecture is consistent: an early, imprecise volume signal, followed by a slower, much more accurate sequence of hormonal signals, gated by exactly how far food has physically traveled down a very long tube. Right now, somewhere, someone is finishing a meal, still not quite full, reaching for one more bite. 20 feet away, literally down the length of their own intestine, a break they've never heard of is already quietly being prepared, waiting for the last of that meal to arrive before it engages. It was never a hormone running late. It was always a question of distance.